When we have a chemical reaction that involves gas as a reactant or as a product, we don't usually measure the gas in terms of its mass because gases are very difficult to weigh. We often specify it in terms of a volume at a particular temperature and pressure. And then we can use the ideal gas law to convert the pressure, the volume, and the temperature to the number of moles. And that's what we did in that experiment where we generated hydrogen gas. You measured the volume of the gas in the eudiometer, and you measured the temperature of the water with a thermometer. So that's probably the same as the temperature of the gas. And then we measured the atmospheric pressure using a barometer. So we have pressure, volume, and temperature. We can calculate the number of moles. And we use the stoichiometric coefficients to convert to other quantities in the reaction. So in the lab example, I can't remember what I'm supposed to write in this blank here, but in the lab example, we had this reaction going on. And we had a mass of magnesium, and so we had grams of magnesium to moles of magnesium to moles of hydrogen gas. And we can calculate the expected or theoretical yield this way using stoichiometry. We could also measure the hydrogen gas and calculate the number of moles and work backward, and we could possibly figure out how much magnesium we started with. That was not one of the problems we did in the experiment, but you could do that. That's using the stoichiometric coefficients to convert to other quantities. Somehow moved my point. There we go. Let's do an example. In this given reaction, 4.58 liters of oxygen were formed at 745 millimeters of mercury and 308 Kelvin. How many grams of silver 1 oxide decomposed? Well, let's write down what we're given. We're given some information about the oxygen. We've got 4.58 liters. We've got 745 millimeters of mercury, and we've got 308 Kelvin. That's all pertaining to the oxygen. And then the question is, how many grams of this? Well, normally with stoichiometry, we would go grams of oxygen to moles of oxygen to moles of Ag2O to grams of Ag2O. Grams to moles to grams, right? Because this is what we're trying to find, grams of Ag2O, and they're giving us information about the oxygen. But this is a gas, and instead of giving us the mass, they gave us the volume, the pressure, and the temperature. So instead of starting with grams of O2, we've got pressure, volume, and temperature of O2. From this information, we can calculate the moles, but we're not going to do it with dimensional analysis. We're going to use the ideal gas law equation. Your expressions right now are just cracking me up. A lot of people are going, What are we doing? I'm sorry. It's okay. It'll be fine. We're gonna practice, well, some people, the Wednesday people had to practice yesterday, but the rest of you get to practice some more in lab this week with the worksheet. If you were in lab yesterday and want to come back tomorrow or Monday, you're very, very welcome to come in and get some help with that, or come to GRASP on Friday, tomorrow morning. Okay, so this is our substitution We're still doing moles to moles in the middle, and we're going to end up with grams. But to find the moles of oxygen, we're going to use the ideal gas law instead. So PV equals nRT, and we rearrange that, N equals PV over RT. R is 0.0821 liter atmospheres per mole Kelvin. So the units on R tell us the units that we need for our pressure, volume, and temperature. The only one that's not good is the pressure. We need to convert this to atmospheres. So I'm just going to do that right up here. 1 atmosphere per 760 millimeters of mercury. So 745 divided by 760. 0.98026 atmospheres. I've got my volume and in liters and my temperature in Kelvin. So I can plug these values into this equation. So pressure, 0.98026 atmospheres. Come on, atmospheres. And the volume was 4.58 liters. R is 0.0821 liter atmospheres per mole Kelvin. Temperature is 308 Kelvin. So 0.98026 times 4.58 divided by 0.0821 divided by 308. And this comes out to be 0.17755 moles of oxygen. Any questions? All the little details can get overwhelming, but the idea, the big idea, is not complicated. We're using this equation to find the number of moles. And then we're going to take moles of oxygen and convert to moles of silver oxide and then grams. I'm going to make some room, so I don't have enough space here. So I'm going to just cross this stuff up here and use the top of the slide. So 0.17755 moles of oxygen. And then I want to go to moles of Ag2O and then to grams of Ag2O. I'm going to divide by moles of oxygen so that the units work out, and I'm going to divide by moles of Ag2O so those units work out. Where do I get numbers for this mole ratio? Yep, from this balanced chemical equation. So there's 2 moles of the silver oxide gives 1 mole of oxygen. So 2 moles of Ag2O, 1 mole of oxygen. How do I convert between grams and moles? Use the periodic table and the chemical formula to find the molar mass. I have a little space down here in the bottom. So 2 times the mass of silver, 107, I believe. Yes, 107.9. Is it not 9?
.868, but rounded up.
Rounded to 9, okay. Because that one's too small, and this one has glare on it, on silver, and I can't see it. 107.9, and then there's one oxygen there, and that's 16. So 107.9 times 2 plus 16, 231.8. So that's the number I put up here, 231.8 grams of silver oxide per mole. So I've put 0.17755 times 2 times 231.8. And this should have 3 significant figures, and so I'm going to have 82.3 grams of silver oxide. And that's the answer. Any questions? This part up here we learned back in chapter 8. And so we're just combining this new idea of using the gas law with this old idea of stoichiometry. We've talked about molar mass, the mass of 1 mole. We also, for gases, have a concept of molar volume, which is the volume of 1 mole at standard temperature and pressure. Standard temperature and pressure is abbreviated STP, and that means 0 degrees Celsius and 1 atmosphere. The freezing point of water and normal atmospheric pressure. I think they chose this because it's a very easy set of conditions to obtain. If you put your flask in an ice water bath and allow it to be in equilibrium with the atmosphere, you've got it. 0 degrees Celsius and 1 atmosphere. So let's calculate what the volume of 1 mole of gas would be under these conditions. So when we rearrange the ideal gas law for N, we get N is PV over RT. So the pressure is, that's not what I'm trying to do. Start over. I'm not solving for N, I'm solving for V. Let's look at that. PV equals nRT. If I want V by itself, I need to divide by P. And the P's cancel out, so I'm just going to erase them. So volume is number of moles times R times T divided by P. So we're calculating the volume of 1 mole, so N is 1 mole, and R is 0.0821 liter atmospheres per mole Kelvin. And what's the temperature at STP? Yeah, we need to use Kelvin, so we're going to take 273 Kelvin. And then we're going to divide by the pressure, 1 atmosphere. So we get 1 times 0.0821 times 273 divided by 1, and we get 22.4. The moles cancel out, the atmospheres cancel out, the kelvins cancel out, and that equals, I'm sorry, doesn't equal, has units of liters. The molar volume of an ideal gas at STP is 22.4 liters per mole. That's the volume of a mole. And this is a very useful conversion factor. I will give you this number on the exam in your useful information section, but you have to remember to go look for it and use it. So what's kind of crazy about gases is that 1 mole of any gas at STP occupies the same volume. It doesn't matter how big the particles are. If we look at helium and xenon, atoms are much larger than helium atoms, but the same number of them occupies the same space, the same volume, 22.4 liters. The mass is different. This is going to weigh 131.3 grams. This one's going to weigh 4 grams. The reason they can occupy the same volume is that there is so much empty space between the particles that the size of the particles doesn't matter. Have I talked to you guys about Idaho? No, it wasn't Idaho, it was Wyoming. I haven't talked about Wyoming either. We drove through Wyoming one summer, and we were looking through the AAA guidebook, and the population of the entire state of Wyoming is about the same as the population of Fresno. Without Clovis, just Fresno. Like 450,000, something like that. You're like, wow. And it's not a tiny state. There's a lot of space. And it was dark when we were driving through. And you could drive for miles and not see a light. Not a single light. And the ranches there have farm lights on their barns and stuff. The houses, they have electricity. But you wouldn't see anything because there was nothing to see. It was just empty. And that reminds me of gases. You're like, wow, that's a stretch. So if you think about people in Wyoming, or you think about people in an elevator, okay, so maybe you put 10 people in an elevator. The one here we have in the science building, I think that's about the maximum capacity. If you put 10 first graders in the elevator, they're going to fit quite comfortably. What if you put 10 of the linebackers from the football team in there? It's going to be really tight, right? The size of the people matters in that small space because there's not a lot of room in between. In the state of Wyoming, if you made all of them giants, if they were all 250 pounds and 6.5 feet tall versus all being first graders, would it matter at all to how crowded they feel? No. There's miles and miles. If you spread the people out equally, they might not even be able to see each other. I mean, it's mind-boggling how much empty space there is in Wyoming. It's beautiful empty space, but it's just like really empty. There's so much empty space in a gas that the size of the particles doesn't matter at all. You could double, triple, quadruple the size of the particles. It doesn't matter because it's mostly empty space. So it doesn't matter what kind of a gas you have. It just matters how many particles you have. That's what matters in terms of taking up space. So let's use molar volume as a conversion factor. How many liters of oxygen at STP are required to form 10.5 grams of water using this reaction? Well, let's organize our information. We've got 10.5 grams of water, and that's the only number in the problem. The question is how many liters of oxygen? So a little question mark, liters. This is where we're starting, where we know something, and this is where we're going, where the question mark is. So normally we would go grams to moles to moles to grams. Hopefully you haven't forgotten that yet. Normally we go grams of H2O to moles of H2O. Stupid thing. H2O. To moles of oxygen to grams of oxygen. That's what we're used to, or should be used to. But we're going to just take a little detour on the end, and we're going to go to liters of oxygen at STP. STP means standard temperature and pressure. That means you can use the shortcut, which is the molar volume of a gas, 22.4 liters per mole. So we're going to start with the grams of water, 10.5 grams of water and we're going to convert to moles of water and moles of oxygen, and then we're going to go directly to liters of oxygen. And we could use the ideal gas law to go from moles to liters, but 22.4 is faster. So then I've got grams of H2O down here, moles of H2O down here, and moles of O2 down there. And my units work out. The molar mass of water is 18.02. You can calculate that from the periodic table. Mole ratio comes from the balanced chemical equation. In front of oxygen, there's nothing. That means there's a 1. In front of water is a 2. And over here, liters and moles, I'm going to use this relationship. It's 22.4 liters is equal to 1 mole. You have to get the 22.4 in the right place. So the 22.4 goes up there. We got 10.5 divided by 18.02 divided by 2 times 22.4. And my answer should have 3 significant figures, so 6.53 liters of oxygen. Any questions?